Today we take a look at open balls, closed balls, and then of course spheres. This is in continuation of what we have started, the discussion we started on metric spaces. We've defined what a metric space is, we know what it is, we've taken examples, we have enjoyed ourselves lots and lots with different examples. So if you have watched our previous videos, I'm sure you would have enjoyed that with us. So we are now very familiar with how to show that a given function is a metric on a given non-empty set. So with that foundation, we want to learn the notion of open balls, closed balls, and spheres. They are otherwise called topological notions. So we will take time and then understand them with examples so we are familiar with them. As usual, we start with definition. So we take x comma d, let this be a metric space. Okay? For arbitrary point, for arbitrary, x naught in capital X, and a given radius or a given number which is positive r bigger than 0. The set, which we denote by b x naught r, and we define it as the collection of all y in capital X such that the distance between y and x naught is strictly smaller than r, is called an open ball. Okay, with center x naught and radius r. So this is what we mean by an open ball centered at the point x naught and radius r. Like I said, it is a set of all those elements in capital X such that when you measure the distance between that element y and x naught, then what you get is smaller than r. Notice that the two parameters x naught and r are given before the definition. So to form the set, you just look at, I take y in x, I measure the distance between y and x naught, I throw it in a given basket, I take another y in x, I measure the distance between y and x naught, I throw it in the same basket, I continue to do this until I exhaust all possible elements of the set capital X, and I measure the distances with x naught. Whatever I get, I throw them in this basket. Once that distance is smaller than r. So at the end of the day, that basket I've created is what I call an open ball with center x naught and radius r. Please, the use of basket is just for illustration. So just to keep in mind how the set we call an open ball is formed. All right. With this definition, let's take some facts that are very direct from this definition. Number one fact is that an open ball with center x naught and radius r is always a subset of the metric space capital X. Another fact is that anytime I take a point z or w as you like, whatever you call the element, if I take a point z in B, x naught r, this simply says that first z belongs to capital X, and then the distance between z and x naught is smaller than r. Like I said before, this r is taken ab initio, so you know what you are looking at. Okay, then another thing that we have to take a look at is that the ball center x naught with radius r is never an empty set. At least we know that x naught is usually in the ball, center x naught with radius. In fact, it is the center of the ball. Therefore, it is never an empty set. And because of that, we can deal with it without fear of am I working with an empty set or not. It is never empty. Okay. Another thing that we need to understand from here is that if I tell you that the distance between a point W and X naught, for instance, or Y naught, or whatever, is smaller than R, what this simply says is that W is a member of the ball, center X naught, and radius R. Okay. So 1, 2, 3, 4 are facts we need to know just from this definition. And once we have them at the back of our minds, we can always deal with them and navigate with them with ease. All right. Another thing we need to look at here is notation. Throughout the discussion on open balls, closed balls, spheres, and of course by implication, other concepts we shall be dealing with, I will be making use of these notations, X naught R, or I write B R, then I put X naught. Any of these two notations mean the same as the other, so that we'll be familiar with this. All right. Another definition we want to take is that of closed ball. And so, like we did before, we take X, D, a metric space. For any point, X naught in capital X, and a given radius or a given positive number R bigger than 0, the set B bar X naught, R, which we define as the collection of all Y in capital X, such that the distance between Y and X naught is less than or equal to R, is called it's called a closed ball. With center X naught and radius R. So this is what we mean by the closed ball with center X naught and radius R. If you look at this definition and then what we had before concerning open balls, we discovered that the difference between this and the previous one is that for closed balls we allow equality. That means the distance between Y and X naught can be equal to R. It can be strictly smaller than R. So when we have this less than or equal to, then we have closed ball. But if we just have strict inequality, we have open ball. Next, we define what we mean by a sphere. So again, we take X comma D, a metric space. For any X naught in capital X and a given positive number R, the sphere with center, the set S X naught R, which we define as collection of all Y in capital X, such that the distance between Y and X naught is exactly equal to R, is called a sphere with center X naught and radius R. So these are the three kinds of balls, if you like, that we have, and we have done the definitions to enable us to understand it deeper and better. We take examples. So the next thing now is to find some examples of an open ball, open balls, closed balls, and so on and so forth.